This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
So welcome everybody to Science on Saturday. I'm Joanna Albala. I'm the manager of the Science Education Program at Lawrence Livermore National Lab. Science on Saturday is a joint collaboration between the lab and the Livermore Valley Unified School District. And today we are honored to have the school board president, Kate Runyon, here to introduce today's speakers. Thank you.
Good morning, and thank you for coming to this year's last of the 4 Science on Saturday presentation. The Lawrence Livermore National Laboratory produces Science on Saturday with the help of scientists and local science educators. A special thank you to Joanna and the production staff for these creative presentations. They work hard to get the best presenters with new and innovative projects for your continuing science education. Please join me in giving them a warm hand of applause. Today, our topic is computer simulations of earthquakes in the San Francisco Bay Area. Most of us know that California and the Bay Area are part of a rich fault area that periodically produces earthquakes, or as some call them, rollers, bone shakers, timblers, or in some cases, how to put everything in your cabinets into the middle of the floor. These earth movement events are hard to predict and to know what kind of damage that will ensue. So in this presentation, Dr. Arthur Rogers, with the help of science educator Dan Burns, will talk about and demonstrate how computational modeling can use information from the past to help understand future earthquakes. Dr. Arthur Rogers is a seismologist geophysicist at Lawrence Livermore National Laboratory. His research interests include computational seismology, earthquake ground motion simulation, underground explosion simulation, seismic discrimination, crustal and lithospheric structure and seismic waveform modeling, and yeah, we're gonna have a spelling test after. Dr. Rogers used Livermore's supercomputers and methods to run detailed ground motion simulation of last year's 6.0 Napa earthquake, the largest to hit the Bay Area since the 6.9 Loma Prieta event in 1989, which I think most of the people in this room were too young to experience. Dan Burns teaches earth and space science at Los Gatos High School and came into teaching from Lockheed Missile Systems in Space and earned a master's in instructional technology. Dan is an avid amateur astronomer, which led to the Huffington Post writing an article about Dan and his YouTube video explaining gravity in a way anyone can understand. So please welcome Art and Dan.
Thank you, Kate. All right, good morning, everybody. Thank you, Kate. Today we're going to talk about earthquakes and seismic waves, and I'm going to tell you a little bit about the work that I do at the lab. My name is Arthur Rogers, and I'm a seismologist at Lawrence Livermore Lab.
And I'm Dan Burns. I'm a science teacher at Los Gatos High School. Thanks for coming.
I want to start out by just talking a little bit about waves. Waves are everywhere in the physical world. And we're familiar with, if we throw a pebble into a pond, we see waves that move out away from that disturbance. And in this case, usually these even, rings that move out. The amplitude or the size of the wave usually gets smaller the farther the wave travels away. There are lots of other examples of waves that are important for radio communications and cell phones. We rely on waves and our knowledge of waves for those as well. And these are rapid variations of electric and magnetic fields that in this oscillatory way. We also know about sound waves, and these have, we typically think of seismic waves are similar to sound waves as the back and forth motions that you can hear me from through sound waves that travel from my mouth, moving the molecules of the air back and forth to your ear, transmitting energy across the theater. The waves that we have in seismology are in a solid material, and we often think about those in terms of slinkies that are shown here. And there's a typical, length scale of waves is the length that the wave repeats itself is the wavelength shown there. In seismology, we have ways to record the ground shaking or the oscillations and vibrations of the Earth in what we call a seismogram, and they're recorded with instruments that we call seismometers or seismographs. All right, well, has anyone here ever felt an earthquake? Probably so, yeah, many people. So this map shows North America with locations that are published by the United States Geologic Survey, which is responsible for reporting on earthquakes and earthquake hazards in the U.S. These are earthquake locations. Each dot represents a location of event in the last 30 days or so. Excuse me, and we can see that the earthquakes are concentrated in some spots, like down in Puerto Rico or in Oklahoma, in the center of the U.S. Excuse me. They're broadly distributed across the western U.S. and in California. And you can see the largest event to occur in this time period is the one in the blue up on the Northern California coast. That was a magnitude 5.7 earthquake that happened about a month ago. Well, if we were to look at this map, a map like this, say 10 years ago, it would look very different. There wouldn't be the earthquakes there in Oklahoma. And does anybody know why we've had earthquakes in the center of the country? Anybody? Just shout it out. Fracking. Wow, very good. How many people went to Roger Ains's talk? Yeah. Oh, very good. All right, well, so fracking is a way to try to enhance energy recovery, oil and gas production, or to take the wastewater that is produced by oil and gas production and inject it deep into the earth. And if you have an earth where there's a pre-existing stress and you put fluids down into the ground and pump them to very high pressure, it can actually cause earthquakes. So they're having a lot of magnitude 3 and smaller earthquakes in Oklahoma as a result of that. All right, well, closer to home, last summer, on August 24th, 2014, at 3:20 in the morning, there was a magnitude 6.1 earthquake in South Napa. And how many people felt? Did anybody feel that event? Yeah, a lot of people. Somebody, you were probably sleeping. Did it wake you up? Yeah, so it woke me up too in Oakland. So let's see, this map shows the location where the earthquake started, which is indicated by the star, and the earthquake ruptured to the north along the fault surface indicated by the black line there. And the intensity of the shaking is represented by the different colors, where the red represents the strongest shaking, then the orange, then the yellow is more moderate, then the green and the blue is weak shaking. And we can see that this kind of follows the behavior we would expect, right? The closer that you are to a source of energy, of wave energy, the stronger the response you would feel. All right, well, talking about earthquakes specifically, there are really three main factors that impact earthquake shaking intensity. First is the size of the earthquake, and in seismology, we measure the size of the earthquake with the earthquake magnitude. And that is sort of a way to measure how strong the earthquake is, and that's related to the length and size of the fault that ruptures, and we'll talk a little bit about faults later, and the amount of slip, how much one side of the fault moves relative to another. Earthquake is motion on a fault. And for large earthquakes, the details of how the earth ruptures strongly impacts the shaking. The other important factor is the distance from the earthquake, right? The closer you are to an earthquake, the stronger the shaking is going to be. Just like the closer you are to a sound speaker, the louder the sound will be. And if we're far away, we'll have less intense shaking. The third factor is more complicated, and that's sort of the energy that the path that the energy takes from the seismic source to a site where we experience the earthquake can impact the style of the shaking because of the geologic structure. The Earth is not homogeneous, it's not uniform, but it has variations in the structure from all the different rock types that make up the Earth. We know there are soils, and there are different rock types. There's harder rock, softer rock, there's surface topography, and these all can impact the shaking. In particular, sedimentary basins, which are flat, softer soils that fill in rock basins, these can amplify the ground shaking, and we'll show some examples of that. Also important are the local soil conditions where you experience the earthquake. All right, well, what is an earthquake? An earthquake is slip on a buried fault. A fault is a pre-existing rupture or pre-existing break between different parts of rock. And they're usually caused by earthquakes happening over many hundreds and thousands and millions of years. Stress builds up between due to motions inside the earth, and that stress gets so high that it gets to the point where it can break the rock. The rock breaks very quickly, and that excites the seismic waves that spread out from the earthquake. So we typically see a picture like this where one side of the fault is being pushed or pulled relative to the other. That builds up the strain. When the earthquake happens, it moves a certain distance, and then the waves travel out from that. And that's also shown in this animation, which is a snapshot from an animation of the 1906 San Francisco earthquake. The San Andreas Fault is indicated by the white line, and the slip on the fault is shown by the yellow colors. And then the white shaded edge shows where the earth is actually starting to rupture, or that's the very tip of the crack that is separating two sides of the fault. On this side, we're on the Pacific plate. On the other side would be the North American plate. And then the red indicates the intensity of the shaking. Well, if we look at maps of where earthquakes occur, and this is a map that shows on a global scale the epicenters or locations of earthquakes of a certain magnitude, probably about magnitude 5 or larger for a long period, decades. We see that earthquakes aren't uniformly distributed across the globe, but they're actually concentrated in linear features or lines that, as where also a lot of other geologic activity like volcanoes and high heat flow is concentrated. Well, this map of earthquake locations defines the tectonic plate boundaries. Right? Many of you have probably studied plate tectonics in your science classes. And the tectonic plates are these large, mostly large pieces of the surface of the earth that move more or less together. And a lot of the motion between the plates occurs on the boundaries, defined by these red lines. And you can see each of the plates are labeled. And the plate boundaries correlate really well with the locations of these earthquakes. Now, in some places, it's very rare to find earthquakes in the center of the plates, but others tend to have earthquakes in the center as well. All right, looking closer to California, this is a map of earthquake locations in California. Each black dot represents an earthquake. And we can see that the earthquakes here also fall along linear features. And in some places, they're more or less just in line. Other places, there are clusters or swarms of earthquakes. These correspond to the earthquake faults we have shown in the map on the right, where the red lines show the major faults cutting through California. In central California, the San Andreas is the only real major fault. But in Southern California, you can see there's a complex network of faults. And similar in the Bay Area, the San Andreas is not the only fault that's important. We have several. And in fact, let's look closer at earthquakes in the Bay Area. This map shows the yellow dots indicate earthquake locations, and the red lines show the faults, and we can see that the earthquakes are concentrated on linear features. Zooming into the Central Bay Area, we see this picture, and you can see, hopefully recognize the area and see that the earthquakes falling on the fault locations. The faults that we have in the Bay Area are the San Andreas that goes along the peninsula and up along the coast, and that is, of course, the major plate boundary. But we also have the Hayward Fault, the Calaveras Fault, and the Greenville Fault. The Hayward Fault stretches from San Jose up through Hayward and Berkeley and Oakland. Calaveras Fault follows along the Highway 680 corridor and into Dublin, Pleasanton, San Ramon, Walnut Creek. And then the Greenville Fault is on the eastern edge of the Livermore Valley, along the hills that bound the Livermore Valley. And the Greenville Fault had 2 earthquakes in 1980. In January 1980, there was a magnitude 5.8 and followed by a magnitude 5.6 3 days later. And that earthquake caused $11 million worth of damage, but $10 million at Lawrence Livermore Lab. So it gave a very strong shaking to the lab, and still presents the same hazard today. All right, well, to study earthquake history and earthquake studies, it's really important, the 1906 San Francisco earthquake. This really marked the beginning of intense study of earthquakes. Some facts about this earthquake is it had a magnitude 7.8. It occurred on the San Andreas Fault. About 3,000 people died from this earthquake, and the earthquake started fires that burned for several days. The shaking was intense from the 1906 earthquake, and you can see the picture on the left, which shows City Hall, which was very strongly damaged by the quake, and you can see the masonry has fallen off the City Hall structure. And then over on the right, you can see the damage. Most of the buildings are uninhabitable. There's lots of debris spread through the streets, and you can see smoke from fires in the distance. This picture shows, again, some of the damage. This is on Sacramento Street, I believe. And you can see the facade of the front of one of that brick building has completely fallen off, and we can see into the rooms that are in that house. The debris is covering the streets. And people are out here watching the fires downtown in San Francisco. And the fires, they burned for days, and they moved up and into this area and spread and caused a lot of damage. In fact, there's people who were killed by the earthquake, but also by the fires as well. And that also highlights an important fact that if shaking damages some of the infrastructure that we rely on, like power, gas, and water, we need that water to put the fires out. There can be sort of mitigating circumstances that can make the consequences of an earthquake more serious. Well, this panorama shows what's left of San Francisco a few days after the earthquake. You can see most of the buildings are completely destroyed and uninhabitable. There's debris spread throughout. There's some damage from fires, and you can still see smoke coming up from the fires as well. So earthquakes are very powerful and capable of causing great destruction. Following the 1906 earthquake, really that began the intense scientific study of earthquakes in America. And there was a professor at UC Berkeley, Andrew Lawson, shown here, and he was commissioned to lead a study to try to collect information about the earthquake effects and document what happened. He published a report along with his coworkers that really provided valuable information that was used to improve our understanding of earthquakes. Also, following the 1906 earthquake, the Seismological Society of America was created. And this is a leading scientific professional organization for earthquake engineers and scientists to get together and share and increase our knowledge of earthquakes. And the Seismological Society of America meets every spring around April 18th, which is the anniversary of the 1906 earthquake. Well, let's look at some of the observations that were made following the 1906 earthquake. And this is a picture showing the surface rupture near Point Reyes, right? So before the earthquake, this was just a grassy pasture, probably just a field. The earthquake, though, separated two parts of the earth at depth, and that motion actually cracked through the ground surface and caused this disruption. And the Lawson report, he sent teams to go out and look for these types of features, and they would follow these features for miles and miles and map it, and map the effects along the earthquake rupture. It turns out in Point Reyes there was actually quite a lot of slip. The motion at depth was almost 10 meters or 30 feet. So it was as if two sides of the earth had moved relative to each other from here, the podium, over to where Dan is standing. Another observation is in this photograph here, which shows a road that crosses the Crystal Springs Reservoir. This is now where Highway 92 crosses the reservoirs. We are standing here on the east side, looking west, and this road used to be straight. But the earthquake occurred, and the section of the road in front, in the background there, moved to the left about 3 feet, right? And you can see by the deflection of the road and of the fence. So this is, again, part of the measurable effects of changes in the surface. And the land, landforms are changed by earthquakes over time. All right, in Point Reyes, again, where there was a lot of slip, here's an example of a fence that was broken, maybe moved about 6 or 10 feet. And again, the fault passed right through that fence and separated those two sides. And you can actually see this location on the earthquake walk over at the Point Reyes Visitor Center today. All right, well, it's interesting to compare two earthquakes. Following the 1906 earthquake, the next largest earthquake that we've had in the Bay Area is the Loma Prieta earthquake in 1989, while the A's and the Giants were playing in the World Series. That caused a lot of damage, including the destruction of the Bay Bridge and the collapse of the Cypress stacked freeway section in Oakland. So some of the statistics on these earthquakes are that the San Francisco 1906 earthquake was a magnitude 7.8, and it ruptured the red line shown in the map there, about 300 miles, and that was, again, mapped by the Lawson report. In contrast, the Loma Prieta earthquake was a smaller earthquake, 6.8, still very large, and it ruptured about a 25-mile segment. And you can see that it actually ruptured part of the part of the fault that ruptured in 1906. And this shows that earthquakes can happen on the same fault, and they can repeat over a certain time period. All right, well, now we're going to talk about waves. Important, again, to the concept that waves are ways to transmit energy across, through time and space. Waves are going to carry energy or on certain amplitude, represented by a variable A. And the waves are going to be a disturbance, goes through space. It's going to travel with a certain speed, represented by a velocity v. And if we go back to our example of throwing a pebble into a pond and having waves move out, those wave fronts are going to move out with a certain wave speed. They're going to carry a certain amplitude, and that amplitude is going to change as the waves spread out and generally decrease. Okay, well, you can also have waves being repetitive motions, right, where we've got a sine wave or a repeating oscillation, and we can measure the repetition of those waves in space with a wavelength, lambda, or in time with the frequency, the number of waves per unit time, number of cycles per unit time, or in terms of the period, the length in time of between the crests of the wave. And these are related where the frequency f would be equal to 1 over the period t. And we have this cartoon then that shows the sine wave as the red there, and it has a certain amplitude a. The crests repeat themselves across space at a wavelength lambda, and the wave crests are going to move with a certain velocity v. In seismology, there are two types of waves that are important. And that is in any solid material, which is different, of course, from a liquid or a gas, right? The air in this room is a gas. It can only support one type of waves, but a solid material can support both types. The first type is a compressional wave. This is a longitudinal wave in that the particle motion is in the same direction of the wave. So and a sound is a good example of this. So as I'm speaking, I'm moving the molecules of the air back and forth, and that travels in the same direction as the back and forth motion. In seismology, these are the primary waves, or the P waves. They're the first waves to arrive. They travel with the fastest speed, and again, they're like sound waves. And a cartoon or an animation of those is shown here. Imagine we have a box full of these particles. They could be air molecules, they could just be balls, and the red line represents a wall that moves each of the particles, and the particles are moving back and forth around a central location, but energy is spread across the box with the wave. All right, shear waves are the second type of wave that we have in seismology. These are transverse waves in that the wave is going to travel in one direction, but the particle motion is going to be perpendicular to that. These travel slower. They're called secondary waves or S waves. And during an earthquake, these waves are responsible for most of the damaging shaking. And an example of a transverse wave is to take a rope or a jump rope and to just flick it, and you move the rope up and down perpendicular to the direction of motion of the wave. And you can see that. All right, so let's look a little bit closer here. Now we're looking at a box full of particles, and the wall, indicated by the gray line, is moving back and forth. And that moves the molecules back and forth. And each particle, and you can follow, there are some red dots there that you can follow that are highlighted. They're basically just moving back and forth about a central position. But the wave is traveling from the left part. Energy is traveling from the left side of the box to the right side of the box. Okay, and we can see a similar example with S waves, where the molecules are moving up and down here, but the crests of the wave are actually moving from left to right, and that's transmitting energy from one side of the box to the other. Well, now Dan is going to do a demonstration of these types of waves.
So we could demonstrate S and P waves with slinkies and ropes and things like that. I thought it'd be more interesting to use the audience to do this. So I'm going to give you instructions here, and we're first going to model a P wave, and you will get to see it up on the screen behind me here. But make sure you listen so you know what to do. So a P wave, the motion of the particles is in the same direction as the motion of the wave. So we're going to start a wave here in the first row and send it back to the last row. So I need everybody to stand up first. We stretch. And then just stick your arms up and put them a little bit forward. And when I say start earthquake, the first row is just going to take their hands and go back. And then when the second row sees that, they take their hands and go back. And the third row and so on. And we'll send it to the back of the room as a P wave. So are you ready? Start earthquake. Whoa. Pretty good, pretty good. And so you can sit back down. So that was, again, a P wave, which is a longitudinal wave. Sound waves are longitudinal waves, too. So this also helps scientists understand other things that work like waves. The secondary wave, or shear wave, or S wave, the motion of the particles is perpendicular to the motion of the wave. So we're going to start the wave again in the first row, and it's going to be more like the stadium wave that you do, except we'll start in the front and go to the back. So you'll just stand up like this and sit down when I say start earthquake. And then you can see the results on the screen. So let's see if we can be a little more in sync here. So first row ready, start earthquake. There you go.
All right. Yeah.
Very good.
All right.
Awesome job. And that did go a little slower, just like in real earthquake waves. And so you were good earthquake wave models. Thank you.
All right. Good job on that. So now we're going to talk about some more details about waves. a seismic event in a solid material is going to generate both types of these waves, P waves and S waves. So imagine a source in a box here indicated by the star, and disturbance has happened, and this is a snapshot of the up and down motion indicated by the different red and blue colors. The white is the background shape. So you can see there's a faint P wave that has sped out in front, and you can see it as the faint ring of the red and blue, and it's followed by a much stronger S wave indicated by the stronger shades of red and blue. If we were to have a seismometer at the location shown in the triangle, what that up and down motion would be as a function of time is shown by the seismogram, or the recorded ground motion, and on the right there. And you can see at early time, first we have the P wave, which goes up and then comes back down, and then that's followed a little bit later by the S wave, with much stronger motion. So the seismogram measures how much the Earth moves as a function of time. If we were to put several sensors out in our computer model there, from close to the source to far away, we would get a picture like this. And this is now showing, as a function of time on the same scale, the closest seismogram on the top to the more distant seismograms on the bottom. And we can see that the motions, they start out and they follow different lines where the P wave is indicated by the blue there and that dashed line. And the S wave is the larger amplitude that follows it at a later time and moves more slowly. So, and you can also see that the P wave becomes very weak. These are plotted on the same scale, and the P wave becomes weaker more faster than the S wave. And that's part of why the earthquake, during an earthquake, the S waves are more damaging. Well, this picture here shows an recorded seismogram from the Napa earthquake. This station was located within the city of Napa, about 5 miles away from the earthquake. And it's plotted in time. It shows a full minute or 60 seconds of the ground motion. And the ground velocity is plotted on the vertical axis. At about 5 seconds, the P wave comes in, and that's indicated. That has a relatively small amplitude. And then about 5 seconds later, the S wave starts to come in, and that's much stronger amplitude. And the shaking continues for about a full minute. And you can see it starts out with very high frequency or rapid oscillations, but then has longer period motions following it. So that is an example of the character of seismic waves that can be recorded. Now Dan is going to demonstrate a seismometer.
So this is a seismometer I have in my classroom. It was built from a kit. If you're interested in making a seismometer, it's definitely something a student can do. Just look up how to make a seismometer. And it's just this bar that's free to swing up and down. And attached to the end of the bar is a horseshoe magnet, this red thing. And then attached to the base is a coil of wire. And so when there's an earthquake, it looks like the bar is shaking up and down, but in reality, the bar stays relatively still, and it's the ground that shakes. And so it moves this coil of wire by the magnet. That generates an electric current. That's what a generator is. A generator moves a coil of wire by a magnet or vice versa, generating an electric current. The stronger the shaking, the more current. And so I have this hooked up to my computer, and it's going to display what the voltage of the current is when there's some shaking. Hopefully it won't be a real earthquake. We'll just simulate one. And so I hit start. And you can see the trace, and it's very sensitive. I've measured earthquakes all around the world with this. If there's a strong earthquake, this will pick it up. Let's see if I can. There's one. Artie, think you can get one? A little bit. The screen almost shakes more. How about this morning? They couldn't do it. How about you guys stomp your feet and see if you can get it to shake? The screen, again, is working like a seismometer as well. And so there are other designs of seismometers, but this is a simple one, and you might consider doing that as a student project. Back to you, Artie.
So There's an important activity now in seismology is the so-called earthquake early warning systems. And the idea with earthquake early warning, it's not earthquake prediction, but is to try to detect, locate, and determine the size of an earthquake after it's happened, but to then be able to broadcast a warning to more distant stations at the speed of light ahead of the shaking that is coming at the speed of S waves. So this systems work really well. There's a test system run by the University of California in Berkeley, and the South Napa earthquake was again located at the location with the red dot. The earthquake was recorded by all the seismic stations indicated by the yellow squares and blue diamonds there. And if we look at one particular station indicated by the blue that's only 3 kilometers away from the hypocenter, you can see that within 10 seconds, most of the shaking has occurred. The 10 seconds are represented by the yellow bar there. So the idea is that if we can have stations that are close to the earthquake that experience the shaking, that they can then be used to determine the magnitude, locate the event, and then we can predict very quickly with modern computers what the shaking is going to be at more distant locations, such as in Berkeley. So the actual seismometer recordings in Berkeley are shown in red, and that's about 35 miles away. And you can see that if we had a warning within 10 seconds, and we could broadcast that to Berkeley, we could provide enough warning before the strong shaking came to Berkeley, and that's indeed what happened. So the idea with earthquake early warning is that you can, we're not going to stop an earthquake from happening. We're not going to predict, at a very specific, at this location, on this time, there's going to be an earthquake. But after an earthquake has started, we can then provide warnings to people who are further away from that earthquake, and that will give them time to get somewhere safe, to be able to take cover. If the BART system uses this to slow down trains if there are shaking coming, so that if you're in the BART tube or something, that you can slow down the trains so they don't get knocked off the tracks. You could have elevators stop at the closest floor and open up, so let people out, so when the power goes down, you're not trapped inside. And there are a lot of important uses for early warning that could be used to save lives. Okay, now we're going to demonstrate, Dan's going to demonstrate trucks traveling at different speeds to represent P and S waves.
And so we'll start these guys off. And so, bam, there's the earthquake. And here's the first seismometer, measures the P wave, then the S wave. Notice how far apart they are. Second station, there's the P wave, still waiting for the S wave. And now they're a lot further apart. And so you can actually figure out how far away the earthquake was by the separation. They don't want to stop. By the separation between the two trucks. The closer you are to the earthquake, the closer together they are. And you can figure out where the earthquake is. And then also this idea when the P wave hits here, there's still time to send warnings to the next station and other places at near the speed of light over the internet or by phone or whatever, and warn them that there's an earthquake coming and give them time to prepare.
Yeah. And that's there are actually active earthquake early warning systems in Japan and Turkey, Mexico City, and other countries. And there is legislation to develop such a system in California. All right. Well, now I'm going to talk a little bit about earthquake shaking and how it depends on geologic structure. And a good example of this is seen in the Napa earthquake. The geology is shown in the left. In map view, and the different colors represents the seismic wave speeds. Slower materials, corresponding to weaker materials like soil and dirt, have lower seismic wave speeds compared to hard rock, which has a higher wave speed. And it turns out softer materials amplify the seismic ground shaking, whereas softer materials amplify the shaking relative to faster materials. Okay, so the earthquake happened at the location of the dot there, and it ruptured along the fault indicated by the black line. And the shaking, which is shown on the right in that same shake map color, where the red indicates the strongest shaking, then yellow is intermediate, and blue is weaker. And you can see that the red follows the Napa Valley, which is underlain by deep sediments, where we have amplification due to the sediments. In fact, in the hills around Napa, we had weaker shaking because the material is not able to amplify the ground motions. So this is an example how geology impacts the wave motion. Another example of this is seen in the Loma Prieta earthquake in 1989. The Cypress Freeway structure was this double-decker freeway that was collapsed, as is seen in the photograph here, very devastating. And but the damage was strongly correlated with the geology. The map shows 3 different types of geologies. The light colors indicate the soft muds, which are very weak materials that amplify the ground motion. The gray scales show sand and gravel, which is intermediate, and the red shows bedrock. And this was very far from the epicenter, so the same type of motion was incident from below, but amplified by surface geology. And you can see with example seismometers here, or seismograms, that the soft mud, the one in the middle there, had the largest amplitude. Those seismograms are shown on the same scale, and we can see there was strong amplification in the soft mud areas. The Cypress structure connected, the 880 freeway there, and the part that collapsed is shown in the dashed line, and the part that collapsed corresponds almost exactly with the soft mud geology there. So it really highlights it's important for us to understand before we build, buildings and where we build buildings, we need to understand what the geology is, because that's going to impact how buildings are going to respond. Another example of that is seen in the 1985 Mexico City earthquake. This earthquake had actually happened on the coast, hundreds of miles away, sent energy into the sedimentary basin that underlies Mexico City, and it caused a lot of damage, a lot of shaking that damaged buildings, but damaged only buildings of a certain size, and not others. And Dan now is going to show an example of building resonance.
So I have some simple models here of 3 different buildings. Number 1, the short building. Number 2, the medium building. Number 2, the tall building. And I'm going to simulate an earthquake here. And I want you to predict which building is going to shake the most. And so how many people think it's going to be building 1? Few. How about building 2, the medium building? Few. How about 3? Oh, almost everybody thinks the tall building. Let's see. Oh, it was the medium building. Oh, no, wait a minute. Oh, it was the tall building. Oh, no, wait. It's the little building. So either you're all correct or you're all wrong. It depends on how I shake it. And so each building has a natural frequency. And if the shaking matches the natural frequency, you get something called resonance. And so if I shake it at the frequency the middle one likes, takes a little practice, its amplitude increases, and that is what caused problems in Mexico City. Certain heights, certain designs of buildings resonated with the earthquake that hit it, and those buildings were damaged more. And so one way we could make buildings safer is to decouple the ground from the building. And so if I put the buildings on rollers here and now cause an earthquake, they shake, but not as much. And so there are buildings in the Bay Area that their foundations are on roller type things, not dry erase markers, but some other things that decouple them from the ground. And so we can make buildings safer by understanding how the ground is going to shake and how that interacts with the buildings.
All right. So the shaking really, the response of buildings really depends on the frequency. So it's helpful for us to know what the character of the ground motion is going to be at a given place. Well, now I'm going to shift to talk a little bit about some of the work we do at Lawrence Livermore. And let's just start with a few points. Fortunately, large earthquakes are infrequent, right? We don't have, a lot of recordings. And specifically, we don't have a lot of seismograms or recordings of very large earthquakes close to the fault. And that's where the damage, of course, is most likely to happen. And we can't know the details of the earthquake rupture in advance. We might know there's a likelihood that this particular fault might have an earthquake, but we can't say exactly what part of the fault or how big it's going to be, and is it going to start from the south to the north or the north to the south, which can impact the shaking. But fortunately, we can use computers to model earthquakes, and we can come up with calculations that represent what we expect the shaking to be, and we can do this in the safety of our computers, right? We can't actually do the experiment of having a large earthquake, but we can simulate that in our computers. So there are different pieces that come together to be able to do computer simulations of earthquakes. One piece is we need a method, and that is both the math and physics that represents what we're trying to model, the excitation and propagation or motion of waves. And we have to write a computer program to do that and take some part of the Earth and represent it into a grid as is shown up here. Some of you actually, there's an equation that represents the motion, and some of you have seen this in a different form. It basically says that rho, which represents the mass density, times the acceleration is equal to the forces that are applied, right? This is just F equals, or ma equals F. Mass times acceleration equals the force, which we solve then for specific to a three-dimensional solid. We also need a model of the source, the earthquake source, and this is a picture of a model of how the Loma Prieta earthquake occurred. The red shows the large amount of slip, and there are two patches that had high slip. And we can then specify how the earthquake, where it starts and how it evolves in time, how much slip occurs from one side of the fault to another. We then use a three-dimensional model of the geologic subsurface that represents the different material properties, the density and the seismic wave speeds of the Earth in the Bay Area, and the USGS has provided a model to do that. And finally, in order to do these calculations with enough resolution to be relevant or to be most realistic, we need to do these calculations on a very large, very powerful parallel computer, or a high-performance computer, HPC. And this is a computer at Livermore, and it involves thousands, hundreds and thousands of processors that are used in a laptop like this one right here, but all connected together and sharing information to be able to step through a calculation. So what we do is we take an area of the Earth, and for a Hayward Fault scenario earthquake that I'll show in a bit, we take a volume that's about 120 kilometers by 180 kilometers, 50 kilometers in depth. We break it into lots of different pieces using billions of points to represent different areas with a grid spacing of 100 or down to maybe 20 or 25 kilometers, or 25 meters, actually. And so we take billions of these points. We specify where, when, and how the earthquake evolves. And for this case, we're going to show a Hayward Fault earthquake, which ruptures along the red line there following the East Bay Hills. And then we step through time solving those equations. The subsurface looks like this. First, the map on the left shows the wave speed according to the color bar there for the surface. And where the warm colors, the yellows and oranges, represent low wave speed materials which represent the sedimentary basins that amplify the motion. And the red or the blue colors represents the harder rock materials. And you can see like the hills south of Livermore in the Diablo Range have high velocity, and that tends to not amplify the motions. If we look at cross sections through the Earth, we can see that there are several low velocity basins that show these dipping sort of bowl-like structures, and that they're often bounded by faults that cut through the region. And you can see that there are strong variations in the material properties as we go from one side of the model to the other at the same depth. All right, this is a picture of the USGS Geologic and seismic 3D model of the Bay Area. And you can see the colors represent different rock types. and that are going to have different material properties, different density and seismic wave speeds that are going to transmit the energy differently. They're usually separated by faults indicated by the red lines there that define the different blocks of materials. And we take this and we put it into our computer model and then calculate the motion. In order to gain confidence that our modeling is correct, we have to validate our calculations. That is, we have to try to see if we can predict motions. And we've done this for the Glen Ellen earthquake. This is a magnitude 4 earthquake that occurred in 2006. An important rule about earthquakes is large earthquakes are infrequently, but smaller ones occur more regularly. And we have several magnitude 4 earthquakes in the Bay Area each year. We can use these and the recordings that are made of these earthquakes to test our modeling. So this earthquake in Glen Ellen was recorded, the location of the event was the white circle there, and it was recorded by the stations indicated by the green triangles. And you can see the wave has moved out to the edge of the box. And again, this isn't like a simple, throwing the pebble and the stone into a pond. We can see that there are a lot of ripples and a complex pattern of the response that's due to the three-dimensional geologic structure that I showed earlier. Well, we've compared the actual seismograms, and this is one comparison at a station in Berkeley. The recorded seismogram is indicated by the blue lines, and the calculated seismogram is shown by the red. And this goes on for quite long, 60 seconds. You can see that we fit the overall amplitude and the timing of the arrival, which gives us confidence that the model is correct. In this case, this shows mostly the shear wave energy. And if the Earth were relatively simple, either homogeneous or just a layer cake model, most of the seismogram would really end after that main pulse of energy at early time. But it's not the case here. Energy travels through the San Pablo Bay, which is a deep basin, and it bounces around, and that causes that long duration ringing that we see at late time. And in fact, you can see in the pattern and the map that the rapid variation and the up and down motion there coming into Berkeley along the San Pablo Bay is related to that late shaking. So now I'm going to show a simulation of a magnitude 7 earthquake on the Hayward Fault. That is a scenario. This is an event. This hasn't happened, but it could. We had a magnitude 6.8 earthquake in 1868 on the Hayward Faults, and of course there were only a few thousand people living in the East Bay then. Now there are 14 million people in the Bay Area, and half of them would be affected by this earthquake. It's going to rupture a section about 60 kilometers along the Hayward Fault, indicated by the white line. The earthquake is going to start underneath Oakland, and we're going to see as we turn to sort of face the fault head on that the fault extends down in depth, but it's not a uniform, it's not a straight plane, but it has some curvature to it. Now the slip is going to be shown, the fault extends down about 15 kilometers or about 10 miles. And the slip is going to be indicated by the purple colors starting right now. And then the ground shaking at the surface is going to be shown with the yellow and reds. So the waves, of course, they move out and away from the fault, but not in a uniform way. We can see that they shake. The shaking is actually stronger on the East Bay because the material is weaker on that side at depth. And then we can see the basins like the San Pablo Basin at the northern end of the Hayward Fault, the Livermore Valley, the whole Tri-Valley area, the Pleasanton, Dublin, Livermore area sits in a basin, and that amplifies the motion. Also down in San Jose, there are two basins on either side, the Cupertino and the Evergreen Basin, and these amplify the motions. And in fact, after the main energy has passed through, the shaking continues in those basins, as you can see here at later times. All right. So that is one possibility for what shaking could be like for a large Hayward Fault earthquake. All right, well, we're always trying to make these calculations more and more realistic and more useful to try to understand the ground shaking. So the animation I showed was done in 2012. Last year, we got access to an even more powerful computer, and we ran the same calculation By comparison, the calculation we did in 2012 involved about 1 billion grid points. Last year, we were able to run on the Vulcan cluster with 55 billion grid points. And the Vulcan, we were able to use 1/3 of the Vulcan machine, and that had over 130,000 CPUs, all working together, solving the same problem. So this shows how we want to keep running simulations with higher and higher resolution. We can, looking at the ground motion, you can see there's more detail in this higher resolution calculation. And we can actually sample the wave field in different places and then use those motions to understand how buildings might respond. So to summarize, earthquakes occur mostly on tectonic plate boundaries and on earthquake faults, including here in Northern California and the Bay Area. And hopefully you've learned something about the faults here in the Bay Area. Earthquake shaking depends on these 3 factors: the size of the earthquake measured by the magnitude, the distance from the earthquake we are, and finally the path and site effects. The geologic material has a strong impact on the shaking. And then lastly, we can model earthquakes using powerful computers. This allows us to perform experiments that we can't do in nature, but we can use our computers to try to simulate these. We can validate against previous earthquakes to try to understand and gain confidence that our modeling is correct and improve our models. And then we can test the various factors that impact earthquake shaking, and this can help us understand the shaking at a specific location. So thank you very much.